Okay, welcome everybody to the top of page 94 in the workbook. This is part C of the exercise that we began in the previous video. So we're still talking about the function f of x equals e to the negative x squared on the interval from 0 to 2, and we're still talking about estimating area under the curve. On the previous page, we did some left and some right sum estimates, and on this page, they're giving us some more data about left and right sum estimates. So starting, for example, with these first two pictures on the left-hand side, a calculator has come up with these two numbers for us. We could, in theory, do these calculations by hand, but there are 10 rectangles involved. That would be a lot of work and a lot of writing. And a computer or a calculator can do these calculations very quickly. Okay, and so the question that I want to throw out there is, based on all the data that they've given us here, 6 different numbers, how would we find the best estimate for the area under the curve? Where would that be? Okay, well, if you think about it and kind of look at the pictures, you'll probably see that the bigger the value of n is, the best estimates that we're going to get. Okay, so the two estimates on the right with 30 rectangles, those should probably give us the best estimates of the area under the curve. So what we could say is that the area is going to be between L30 and R30. Okay, in other words, between 0.915 and 0.849. And you might have also noticed that in the left sum, the rectangles stick out above the curve a little bit, so that number is going to be a little bit too big. And the right sum, those rectangles are below the curve a little bit, so that number is a little bit too small. So if we wanted to be even more accurate, what we might do is just take an average of those two numbers. So taking the average of L30 and R30 yields an area estimate of 0.849 plus 0.915 over 2. Okay, and you can calculate that out and notice that you're going to come up with 0.882. So that number is probably the most accurate area estimate that we can get based on the data that we have above. Okay, now I want to step back from this and just make a more general observation here. Okay, so as you look at all this data and all these pictures that we have, you might notice that as the value of n increases, we started with 10, then we went to 20, we went to 30. The bigger that value of n is, the closer we get to the area under the curve. Does that process remind you of anything from earlier in the course that we studied? So this idea of approaching the area under the curve as n gets large, that might remind you of a limit. And that's really what's going on here. We're taking a limit of areas of rectangles and approaching the exact area under the curve. So we could make a note down here that the exact area under f of x from 0 to 2 can be thought of as a limit of our left sums and our right sums. Both of those are going to get closer to that area as n gets larger. Okay, so that brings us to one of the biggest definitions in the entire course. Okay, the idea of the definite integral of a function. Okay, how is this defined? Well, the same way that we just made the definition in the note here, the definite integral of a function is just the limit of the left and the right-hand sums. Okay, so it's a way of representing exact area. Okay, and it has a special notation that we're seeing for the first time. The definite integral, we're going to write using this notation that I'm circling. So that strange S-looking symbol, that's just the integral sign, and the way that we would read this in words is the integral from a to b, that's the interval, of f of x dx. Okay, and those words are just a way of talking about the exact area under a curve. That's what that symbol represents. Okay, so if we move just to the next page here, this is the very last part of this example. Okay, example 2 asks us to use the result of example 1 to estimate the integral from 0 to 2 of e to the negative x squared dx. That function, e to the negative x squared, is the same function that we used in example 1. Okay, well, what does all of this mean? Well, again, this definite integral is just a way of representing and talking about the exact area under a curve. So in words, this is just asking us, what is the exact area under f of x on the interval 0 less than or equal to x less than or equal to 2? The 0 and the 2 are just telling us the interval that we're talking about. Well, we estimated this area on the previous page. We decided that taking the average of L30 and R30 gave us the best estimate. So this is approximately L30 plus R30 over 2. We already did this calculation on the previous page. Nothing different here. And we're still going to get the same number of 0.882. Okay, so there's really nothing different in this calculation that we did other than the fact that we introduced a new way of describing it. This notation, this integral, is just a way of representing this number, this exact area under the curve. And in the future examples, we'll continue working with this notation and using it as a way of helping us estimate area.